Can you change slides? Good afternoon, sir. Good afternoon, everyone. Tentative. Yeah. Back. First, yes, titles. The tentative title for our project is Emergence of Skills via Grafting. I'm Bhagwan, Dhruvi, and Parth. Will present in this order. Our TA mentor is Prateek. Next slide. The pre-training loss is very predictable given the model and the data sizes, and this comes from the scaling loss, uh, where y is the loss and x is the scaling parameter. So it's generally formulated as a power law. And when we fix the training corpus, as we increase the model size, which is either the hidden size of the model or the number of transformer blocks. So when you change the size and each model is trained to convergence, you get this power law sort of equation. And the other method is when you fix the model and the data distribution and train the model with a different number of tokens, and we still get this power law distribution. So here n is the number of parameters and d is the number of tokens used. And with respect to both of these, loss is governed using power law. This is the famous Chinchilla scaling law, where loss has an exact form in terms of power law equation with respect to n and d. These constants will change with respect to different models. Like llama will have a different llama series will have a different constants, etc. So while the pre-training loss is very predictable using the power law sort of equation, the downstream task performance is not so predictable. Downstream task means, I mean, the common benchmarks that we have over the pre-training LLMs like MMLU, MMLU, GSM8K, etc. So what they observe is that uh, there is a certain scale limit before which there is a trivial accuracy, trivial performance on these tasks. And once the scale limit is reached, there is a non-trivial accuracy or performance on the task. One small note is that emergence is a purely pre-training phenomena. No fine-tuning is involved. So something like in-context learning, few-shot prompting is an emergence phenomena. So we're not training the model to see few examples and then answer the next one. Model is learning while pre-training itself. So commonly these benchmarks will have training, test, validation, and test. But though the model never sees the train samples, we give few short examples from the train and we evaluate these pre-train checkpoints on the test set. And this is how we plot that emergence curve, which is not exactly ReLU. It is nearly flat over here, and there is non-trivial performance after this emergence point. There's a small background for the paper I'll present. This gives emergence from a loss perspective. So till now we saw emergence from N and D, which is model parameters and data tokens. So this new paper tells from a loss perspective that since loss is dependent on both N and D, we can formulate the scale parameter as loss. So downstream task performance, the normalized one, is zero, not exactly zero, only the trivial performance of trivial performance before some threshold. And when loss is less than a particular threshold, then we have then the performance becomes predictable in terms of the loss. This is regardless of the model size or the number of tokens. So keeping the data distribution and the tokenization constant, they empirically tested with different architectures like Llama, Pythia, etc., and found that regardless of what data size or model size you use, when the architecture and the data distribution is constant, loss uniquely defines the performance on the downstream tasks. Yeah. So when you want to compare different models, so this is for a particular architecture and particular data distribution. When you want to compare different models, so one suggestion that they gave is that we can use the common public validation text validation set, because now data distribution is same for both of them, and normalize perplexity instead of the training loss. So this way we can compare different models and their downstream performance. Uh, so one important problem statement is to predict emergence. So generally, uh, so the problem is that when you have small scale models, it performs nearly random, and you want to know at what point this emergence happens using the small models. So the goal of the paper is that this assuming this is the actual emergence point in loss. So right now we are using the scale as loss, like how the previous paper suggested. So we want a way in which we can shift the emergence curve to small models. So that's the first step, shifting the emergence threshold to small models. Then we want to model this emergence curve, means at what point this emergence happens. And then we want to, that will explain, so the three steps. Yeah, no, this is a decreasing, I didn't mention that. So as loss decreases, I mean, at this point we have emergence. We want for a smaller model the emergence to occur. And then we want to model the emergence and extrapolate it to the few shot setting. Next slide. So they tried different mechanisms. It's more of experimental based. So they tried different methods of shifting. Like for example, for MMLU, 5 shot is the standard. So they tried to increase the number of few shot prompts, and that didn't shift the emergence curve. And they tried prefix tuning, etc. But finally, they found only when they update the parameters of the model they could shift. So one thing is fine tuning. So for example, MMLU or any benchmark, they have train val and test, but only test is being used for evaluation. So the train test which remains, they tried training with different data fractions. So taking half of the training samples available, and when they fine tune each and every checkpoint, they found that the emergence curve shifted. So the stars are the few shot emergence curve. Now yellow is 1/16th of the data fraction. The train samples, when they taken fine tune, they found that this emergence curve shifted to the lower losses, sorry, higher losses, means small scale models. And as this data fraction keeps increasing, emergence curve shifts to higher losses, which means smaller models. And now when we can, that fine tuning train, which is used for fine tuning. No, sir, no, sir. So these are say pre-trained checkpoints, and these are few shot results for it. So for each and every loss, we have a star, and when you do few shot accuracy, these stars are coming. And now uh, we are actually fine tuning them, sir. Yeah. So assuming something like MMLU has fine tuning. Yeah, yeah. So something like if you have 2000 samples per MMLU, uh, yeah. So basically, each of these the x-axis is different checkpoints. So the checkpoints taken at different losses. Now these stars are few shot prompt accuracies for the task. Now, like if the task is MMLU and it has 2000 samples, uh, so if you take 1/4 of the number of training samples available, so something like 500 samples if you take, and fine tune each of these checkpoints, and then evaluate on the eval set. So from train, we take only 500 samples and fine tune each. Yes, sir. If yes, sir. The stars are few shot. The circles are fine-tuned. Yes, sir. Yeah. So basically, a training on the particular task, so the emergence curve is being shifted. Yeah, yes, sir. The smaller the pre-training loss. Yeah. So we are taking a model series, like llama series. So for example, they performed experiments on open llama. So there are 3 billion, 7 billion, and I think 13 billion. Yeah. The data distribution is same. So they found that for 3 billion model, none of the tasks emerged. So all of them will be somewhere over here only. So the pre-training loss never actually decreased less than 2.2 when they trained the 3 billion open llama model. Only for 7 and 13 billion open llama models, the pre-training loss went as low as 1.8. And that time for those checkpoints, when they evaluated thought on the benchmarks, they found more accuracy. Larger, sir. So that's what the previous background was about. Before, scaling laws were all about N or D, but now I'm telling we can take loss also as the scaling law. Like loss is a function of N and D from scaling laws. So the Newton's paper told we can actually use loss also to, yeah. So right now loss is in the x-axis. Like all these checkpoints need not be from the same models, from the same loss. Like for example, this 1.8 loss, one of them could be from 7 billion model, one of them from 13 billion model. So right now, loss is the governing factor. Yeah. So if you when you so forget about what is the model size or data size. If you just take a checkpoint and its loss. Now, if you take few shot prompt accuracies, this is the emergence curve that we get. It happens somewhere around two. I mean, when the pre-training loss is two. Now, for each of the emergence is the sudden spike. Like before, it was a very trivial accuracy of zero, and once that's what emergence means. Something which happens, which does not happen at a small scale models, and it happens abruptly in the larger scale models. Yeah. So when we fine tune on different amount of fine tune train data, and evaluation happens on the same test set. Then they're finding that accuracy, the emergence curve shifts to the right. We're not fixing models, we're fixing the model series, something like llama series. So the architecture remains same, the data distribution remains same. Uh, yeah. So basically, the background manage. Go to the background slide. Yeah. So this one says that when you have data distribution, tokenization, and the architecture constant, then regardless of the model size and the number of training tokens, the N and D, the loss uniquely governs the performance. So, like for example, a 2.2 loss, if you'll take, okay. So right, rarely series is not coming. It's only loss is coming. So assuming 2 is the loss here. Now we have the scaling law L equals to 1 by n power and 1 by d power. So different n and d combinations can give the same loss. So that's what the series is coming. So no, sir. There is no series here. Then. Shift is for the task, and the pre-training losses are for the series. Like regardless of this, like just for they're giving one series, like we're taking the data distribution and the architecture constant. That's what I'm talking about the series. The data distribution, like from where the data is coming. Yeah, yeah, yeah. Yes, sir. The shift is that this emergence was supposed to happen at this point. Now, for each checkpoint, when you when you fine tune on the different fractions of data, this emergence curve shifts to the right. Like something like if you train on full training data, like if you fine tune on the full train data, then emergence happens over here itself. So at a lower loss point, sorry, higher loss point. Here, higher loss point means it's for smaller models itself. Yeah, so is yes. No, basically we are trying to see that we can shift this. Yeah. So basically we're trying to model this emergence point. Yeah, shift is obvious. It's just that the shift, like it does happen when you try different things, like increasing the number of shots, the shift didn't happen. Like giving some 20 examples. That way the, yeah. Hmm. Next. So now they're trying to model the curve. So they're modeling using a ReLU, so because they mainly want to model that point. So E is the emergence point at where it happens. L is the loss, and performance is the performance that we get. Now they're trying to fit a ReLU type of curves for that. And now the emergence point is depending on the data. Like as data fraction, I mean number of samples, training samples are changing. We're having different E's. So now they're modeling E using power law sort of this power law equation with respect to D. Now we have these parameters A, B, E, K, alpha, C. LM is the loss. So D is the data fraction, number of samples, fine tuning it. So right now our input is the number of fine tuning data samples, the loss, and our target is the performance. C, C is just a parameter here. So with this input and target and these parameters, we use maximum likelihood principle using MSc loss fit, and the optimizer is LBFGS. So using these, they fit all these parameters. Not this. This E will get substituted here. Yeah. Basically, that the king should come at E. So we are shifting the ReLU. Yeah, yes, sir. Like we saw, as the data fraction changes, the emergence curve shifts. So emergence point is a function of D. No, this exact particle gets performance we're modeling as a ReLU, and this E. No, sir. LM is the loss. E is when the kink happens. Depends on depends when your LM or when your LM is then your emergence happens earlier. We'll go back. Like here, regardless of the model is formed. Yes. Then the emergence happens much later. But I am never taking this. So how can LM not be that much emergent? So what they take away from this? So this the takeaway from here is that when you are fine tuning from different D, there's some emergence. Emergence is a single point. There's an emergence gradient also. Okay. Isn't emergent? Yeah, LM. If the LM is high, which means since it was small, capacity is small. Yes, sir. What goes on? No, we are telling loss totally governs the model size. So we get the model sizes only based on losses. Yes, sir. Emergence is pushed toward the lower data fraction. Loss is low here. Yeah. Emergence is like loss is where I mean basically when yeah. Incredibly low. Yes, sir. The emergence is also pushed to orange these points. So basically here we fine tune on some amount of data, and that's why we are able to shift it. LMS. Emergence is pushed to lower. Emergence happens at lower data. When the loss LM is higher, the emergence is at higher rate. The loss is higher, LM happens at yes, sir. I mean, that's your critique. Well, the loss, the data fraction that's required is the same. Here, if my advantage is here, trying to model how much more data we will need to achieve the same accuracy, given a lower loss. We're trying to model the king equal from the loss. That is what we're trying to estimate the data estimate that to reach that same accuracy. Okay, so the purpose is different. This is when we change the take home from the state. As per the we can have different take the state. Are you going to model the yeah. Yes, I mean, this is a function of B. B is not out. B is Yeah, so finally, they're trying to predict this point where the actual emergence happens. And now the assumption is like fine tuning is like a generalization of few shot. So fine tuning, you're training on multiple samples, and few shot only five or so. So since we have E as a function of D, and now once we fit all the parameters, if you substitute D equals to the number of few shot samples, we get E. E is the point at which, uh, yes, sir. And that's how they get the point at which the emergence happens. Next slide. Uh, like OpenLlama series gives intermediate checkpoints for 3, 7, and 13. Using only three, they estimated for each task at what loss. Uh, that's it. Sir. Using 3 billion model, they're able to find the emergence point for 7 and 13. Basically, using 3 billion, we have those checkpoints. Where one slide back. So using 3 billion models, maybe you never get this point. Like you never reach these losses itself. So you only fine tune and get these curves. And when you extrapolate, you get at what loss the emergence happens. And then when they verified with the bigger models, they found that actually at this loss the emergence happened. Yeah, that's it about it. What? Look, OpenLlama already is the point. We only need to fine tune the computer change already.
Yeah, hello. So I would be presenting another paper, which again is another method to learn where exactly emergence occurs in models. Next slide. So yeah, that's the background for this paper that we need to find out. So they propose that the skills which a model learns are localized in the sense that there are a certain subset of parameters within a model which are the only contributors to make that model learn that particular skill. So we introduce the concept of grafting, wherein we try to identify which parts try to identify a mask which gives us the subset of parameters in the fine-tuned model which are actually responsible in giving the skill to that fine-tuned model, and then we just take those parameters from the fine-tuned model and we leave the remaining parameters as they were in the pre-trained model. And the final grafted model which we get is ideally it is supposed to, it does give us better performance in a variety of tasks like um, accuracy and also in other domains like generalization, calibration, etc. Next slide. So yeah, as I just pictorially introduced in the previous slide, uh, we so we have two models, the pre-trained one and the fine-tuned one, and we intend to learn a sparse mask, which is indicative of the parameters of the in the fine-tuned model, which are responsible for the skill. And so this is how we model the this is how the equation for the grafted model. So we want the gamma, the mask, to be sparse, and also the performance of the grafted model should be comparable to the fine-tuned model. Next slide. So here is how we try to learn the mask. So ideally, we want the mask to be binary and sparse. So we want a minimal L0 norm for the grafting mask. However, for optimization, um, we model the grafting mask by this equation. So we are building a final grafting mask on top of a base mask. So in most of the experiments, we take the base mask to be the top K parameters which change during fine tuning. And so that is the um, so that is going to so the base mask is supposed to be sparse in that way. And then for training the final mask, we basically train this S vector. So um, so the sparse so from by using this equation, we ensure that the yeah that I mean component wise multiplication. So this is how we are modeling the final mask, and S is the parameter which yes, the base mask is basically the top K parameters. So it is one in the places where um, for the top K parameters which have changed from pre-training to fine tuning, and it's zero elsewhere. Yeah, maximal change. Yeah, because we are kind of thinking that the parameters which change the most are going to contribute to that to the learning of that skill. Not all. No, no. Yeah. Yes. So it's a vector. It's of the size of the model. Yeah. Although we are still initializing it so that it's almost so that sigmoid of S is like having many zeros, like it's close to the zero vector because we want sigmoid of S to be sparse. So yeah, next slide. So yeah, that was so like yeah, this is the experimental setup, and they have yeah. So yeah, so the grafting mask. I mean, the observation is that the model is able to learn the core skills, and we also come to know that this skill is actually localized. So, like, even if we do things like taking union of masks or overlap of masks, so then we find that. And also, next slide. Yeah, multi-task and continual learning. So, like, even in the continual learning premise where you are fine tuning the model on a series of tasks sequentially, we find that no, yeah, yeah. So, like, some of the questions that arise as an extension to what could be done uh, after this paper was to check whether all skills are localizable because they have um, done the experiments only for classification tasks. Checking whether skill localization holds for all skills and if the graph could be learned during the fine tuning itself without training. Yeah, so which we kind of will address in here.
So this paper tries to predict emergence as well, but they realized one thing is that modeling emergence in an LLM setting is expensive. So what they do is they basically construct a very quanta model sort of a setting, They tried to model emergence through a neural network by replicating the same thing or basically predicting it through a multilinear model. Next slide. There's no grafting. So this is the hypothesis that took place. Yeah, yeah, we should. So what this basically the basic hypothesis is any neural net will basically learn in a power law setting given the data points, number of parameters, and the compute. And compute can be represented in terms of the number of inputs and the number of models and number of parameters as a multiplication. That's the simple power law definition there. So yeah, next. So the only reason why they used a multilinear model and a two-layered neural network is because of its tractability. So this is the model that they use to compare against to model emergence. So it's just 1,000 neuron layer there and then just one output layer there. And this is just a flattening which came out as a function that I used to plot the. Yeah, next. So this is the multitask sparsity, multitask sparse parity data set. So let's explain this in a better way. Let's go ahead. All right. Next. So we have a total of ns number of skills, and each ns number of skills is associated with a one hot encode. Now, next slide. Now next slide. Each skill is associated with a mask. This is the relevant bits, and it is fixed. No, multiple skills. And these skills are represented by a one hot encoding. They are called control bits. Each skill is associated with a mask. And this mask, if you notice the X is over there, these are the mask. And NB is the size of the input bits. Next. Now, as you get the input bits, what happens is you apply the mask on top of those input bits, and now you get these highlighted red bits, which is it's a random. It's randomly sampled only once for each skill. That mask is retained for each skill. Yes, it is fixed for each skill. It's just applied for every input given the skill. So given an input, given a skill, there'll be a fixed mask, which is then applied on the input, and then this is the modified input. So this MIX is the highlighted bits from that, which came from the mask. So that is the input bit. Then we learn. Yeah, so we'll see what exactly. Sorry.
The representation of the skill will change, right?
Yeah.
The representation
Yes.
is based on the
Simple.
masks.
So yes, so we ensure orthogonality in the final set. So if you see here, so the main objective of this multitask flexibility is to maintain orthogonality in the basis function. So they're trying to represent every skill as a basis. So what happens is, if you just go one slide next. Yeah, they are random. In this setting, yeah. I took a look at their code and they're just using a random distribution. I think so, because now if we have, let's say, two tasks which have the same mask, no matter what you give them, yeah, whatever you give them, it's going to end up in the same label. But then that is what is ensured by this final transformation. So this final transformation, what happens is, so this is this matrix, which is constructed. There's a number of skills, and these are the data samples. Now, on the y-axis, we will have the control bits and the input bits. Now, this is active if and only if the control bit is equal to the basis function. For others, it will not be active. And then this is just like a XOR. So you just XOR over them. -1 to the power. So if it's positive, so it's going to be 1. If it's negative, it's 10. Now, yeah, next slide. So let's move slides. So this is the guarantee that if k and k dash are not the same, then they'll be orthogonal. Because if I is not equal to k, then it will be 0. If I is not equal to k dash, it will be 0. And if I is equal to k is not equal to k dash, it will be 0. So it can never be that we're not ensuring orthogonality. This is important. Why? This is important in two ways. Further, when we progress, the loss is decoupled. For each skill basis function, the loss is decoupled. Secondly, you cannot say that if I have learned the skill for, let's say, skill, I don't have I mean, there cannot exist another skill J, which you can perform good only by learning I. So you'll have to learn the skill functions for all the K. all the n steps. Just move 2 slides back. So here we're saying that while we are constructing the multitask sparse parity data sets, each skill is sampled from a power law distribution where alpha is 0.6. This is being empirically arrived on. There is no proof for that. Now, the reason for using a power law distribution is we want to later also notice that as the number of samples for a given task increases, the loss converges faster. And if the number of samples are less, it will take more time for the loss to converge for that specific task, or in general for it to converge. And the input bits are randomly sampled, I mean, from a uniform distribution. So this is next. Next. Yes. So this is the final objective that we want to ideally learn. So these can be thought of as the label against which the MLP. S is a constant, some scaling constant, and gk I comma x is for the kth skill given the control bits I and the input what is the value. Now this will be either s or minus s because for any other k, if I is not equal to k, it will be 0. So only for I equal to k, it will be either s or minus s. Now this is this normal mean squared error loss. Now what we do is we try to write since we have an expectation term over there, we use the probability distribution from which the skills were selected as a term over there. So move forward. Yeah. So they define something which is called as a skill strength. The skill strength is basically an expectation over the actual skill basis function and what the model learned. And the expected value of this will be s square. Yeah, s. Yeah. Move much later. Yes. So the maximum value of this will be s because these will be 1 or minus 1. The model should learn the s as well. So if it arrives at this equation, which means it becomes completely aligned to what we want to learn, the maximum value will be s. So it is just a note for the coming plots that if we just divide rk by s, it will be normalized to 1 because it never exceeds 1. Never exceeds s. Next slide. Yes. So this is their multilinear model that they've proposed. A and B belong to this vector set of size n, and this is t means the model at timestamp t, and AK, BK, TK. These are the parameters that you're trying to learn. Next slide. So basically the whole point of having AK, BK is to represent something similar to the structure layer of a neuron because they're trying to compare it to a two-layered neuron. Now, AK and BK needs to map to S. It needs to learn how to reach S because advantage that this has over the neural network is that it has the basis function. The neural network will not be provided. Now, yeah, N is the top most frequently appearing skills, which comes from the corporate distribution. Yeah, A and B come from. So that N is something that we will test on. So how many frequently appearing skills do you want the model learns to emerge? So let's say if your N is a very small number, which means that you're not learning that frequent. So as you have more, so classically any neural network will pick up patterns for a more appearing skill than for which is not appearing that frequently. This is that parameter which models. We want to keep testing over multiple things to model that emergence. Yes. So this is the classic loss. So this basically arrives from if you just go 2 steps back, 3 steps back. One more step. Yeah. So here, if you see this loss, and if you write it in terms of the LK, this first equation LK 1 by 2 EX, and if you expand the F star as multiplication GK, you will arrive at 4 steps forward. Yeah, you will arrive at the same equation. Now, if you proceed further, so this is the loss that the multilinear model wants to learn. one step forward. Great. Now, if you use, so there are three tools that are used to arrive at this specific, the loss that we saw in the last page, and the expectation terms from the loss in the neural network page. Now, one thing is we're trying to learn the multilinear model in a gradient flow. So that gives us the ability to do a normal gradient design. But then the good thing is, if you focus on the first equation, sorry, go one step back. Step back. Yeah, if you notice here, the losses are decoupled. It's like the kth skill is only going to be considered concerned with its own ak and bk value. That's all. Move forward to. That is why, because of this decoupling, we can write the derivative of ak and derivative of bk separately, and then we can take the derivative of rk, which will expand in the terms of ak and bk. Now, if you shift slides, and then it becomes a normal ordinary differential equation. Now, if you just integrate it from time step 0 to time step t, you will arrive at this last stage. So this basically represents the normalized skill strength that we have. So this is how they've arrived from this decoupled loss to this skill strength representation, which is now very easy because you know the skill strength at time step 0, you know S, and you know the time step t. RK basically measures is for the number of skills that are currently present, what is the kind of score that you would want to give in terms of the model accuracy. So if you go 5 steps back. Yeah. Yeah. Okay. Next. So now they're trying to come to this scaling law from here. So now, if you see, so we use this equation, and the equation from the last step. Now, for n, we have n most frequently appearing skills, which means that the model would have completely learned, the multilinear model would have completely learned the n skills, but post that, it would have 0 accuracy on that, which means that we can take RK as 0, which means that this term goes away. Right? This term completely cancels out because of the expectation term we had. And then just normal algebraic expansion, and you would arrive at this. And there are certain assumptions is that the number of samples that you take from each skills should also follow the same probability distribution as the skills. So these are the key takeaways, is that the time scaling loss is modeled as a power law decay of the time because it's in its denominator. The data scaling loss is directly dependent to only the observations of the kth skill, and the parameter scaling loss is also a power law decay in n. Because as you increase the n, this loss is going to decrease because this term is going to go up and this is going to completely vanish out. Yeah. Right. So this was 62-page paper. So I had to condense this. So this is where they tried to model the time emergence. Now, yeah. So the key takeaway is to their smaller model, which is this calibrated over just a single skill, that can model the emergence for a two-layer neural network for a number of skills of 5. NS is 5. It can model all of them across time step t. So after this point, we see that yeah, I mean, most of their examples are yeah, it's about arriving at that closed form equation, which can be directly substituted and plotted in the graph. And can model it. There is a transformer experiment, but not with any LLMs. So this is for the time. Next, this is for the data emergence. As you increase the number of these that you can sample from the entire skill set, it can also model. Also, now since our neural network, yeah, I mean, just one step back. We just add another DC short parameter into the MLM formulation so that we have to learn at least DC steps to reach in that. So this is about parameter emergence, and we can see that in a standard deviation of I think 1, we are able to model the neural network emergence. So this is their experiments with transformers, and I think they were able to also model that strict growth in skill strength which they've quantified. And so this tau emerges when RK is sufficiently larger than 0, and they see that even that increases as the number of skills increases.
Small background about before the proposal is that there's one more paper which connects blocking, emergence skills, etc. So the key idea is that there are distinct circuits in the neural network, one for memory, some for memorization, some for generalization. And when you have a pure memorization task in a multitask setting, the memorization dominates, and since there is no generalization component for the memorization task, only when model scales to a certain extent, it allocates parameters for the generalization circuit, and that's how it will start generalizing when the model scale. So the key idea is that there are specific it will come through grafting only. Finally, emergence of skills through grafting only. The key idea is that it is localized, like only some specific neurons are. Like we won't go to the specifics of the circuit first. Next week. No, circuits is actually coming. Yeah. So basically, that LLM training is also a multitask setting where many memorization tasks are involved. And since emergence is happening at scale, we are claiming that only specific parameter neurons are responsible for emergence to happen. So the idea is that if this is the like from the first paper that I presented, if this is the loss threshold, no, if this is the loss threshold at which emergence happens, and if you take a pre-emergence checkpoint and a post-emergence checkpoint, if you can graft C2 onto C1, we claim that the performance on the task for C1 will also improve. So basically, grafting is an alternative to check whether something is localized. Like fine tuning was localized, and that's why when you grafted a fine tuned checkpoint to a pre trained checkpoint, we could get the same performance. So similarly, we claim that emergence is also localized, and if you emergence is basically that when it comes to, since we have multiple checkpoints, we do LM eval harness for each of them and plot the accuracy curve. So wherever we have this kink, we know that emergence happened. Uh, we're not finally detecting emergence, but we are trying to see whether emergence can be influenced upon something earlier. Just once, something like uh, uh, the idea is that uh, if this is the like this is loss, even if we'll take 7 billion parameter model, so there's just one model, and if this is a post-emergence checkpoint C2, and this is a pre-emergence checkpoint, we want to see whether when we graph C, so this is the performance curve that we get, something like this. So we want to see accuracy on the task T. So we want to see when you graph C2 onto the C, whether the performance of C increases because the emergence which happens is localized. And for the graph mask, we get from fine tuning C. So we fine tune C on the task and we get the graph mask using the method that she mentioned. And using the graph mask when you graph this. And last thing is that similar to the curves that we got, if you take a later checkpoint, we should get a higher. And similarly, if you do the same thing for earlier checkpoints, we'll get the same shift of emergence curves. Yes.